but not so much that you won't have, you'll have to still have to work. You know?
I'll give you $1 billion. That's all you need in pennies. So have fun dealing with that, children.
I take it.
Take it, yeah.
4 trucks.
Now, there's so many trucks, I don't even know. $100 in pennies is already a lot of pennies. I can't imagine how many $1 billion in pennies.
Like, just like, no, get out.
No. It's like we don't have enough copper.
Okay, so the last thing we have time for, it's not the last thing I would like to do, but it's the last thing we have time for, is basically what I just did over there on the screen, but not a toy version. A real system of a whole bunch of identical fermions. And we're just going to look at the behavior of the ground state. We're not even going to do the excitons like we did in that example, where we had Q of 1, 2, 3, 4, 5, 6. We're just going to look at the ground state. Okay? So we're going to do an application of quantum statistics, what is called the degenerate Fermi gas. I'm going to have to do a slightly abridged version of this. So what I'll do is I'll scan these few pages in my notes and I'll put them up on Blackboard so you can see in more detail. Okay? But what we're doing here, just to set it up, let me remind you, or let me tell you, we'll have n non-interacting identical fermions. So in that they're non-interacting, that's what we mean by a gas. Okay? Like the ideal gas assumes no interactions between the particles. Okay? Also, we're in the condition, we're in the situation where a semi-classical analysis, the condition for a semi-classical analysis is not met, meaning the quantum volume is not much less than the volume per particle. Okay? So a couple of systems for which you might have to deal with this, all right, are conduction electrons in a metal. We'll even put the metal at room temperature. In fact, the temperature of a warm room, 300 Kelvin. So you certainly, by human standards, would not call this a low temperature system. Okay? And you might expect, at such high temperatures, that a semi-classical approach would work. But here's what you got to do. You got to calculate the quantum volume for the conduction electrons, h over the square root of 2 pi mass of an electron times t, all cubed. And you get 4.3 nanometers cubed, or 79.5 nanometers cubed. That's the quantum volume for conduction electrons at a temperature of 300 Kelvin. And let's take a specific metal. How about copper? You can look up the particle. Notice this is the inverse of the electron density. Volume per electron, so invert that, it's the number of electrons per unit volume. You can look up what that is in metals. Okay? And so then you can get from that the volume per particle. And what is it in copper? It is 0.2 nanometers quantity cubed, which is 0.008 nanometers cubed. Notice the quantum volume is actually considerably larger than the volume per conduction electron. So the wave functions for these conduction electrons are all overlapping each other. It's a vast tangle, okay? And you are not in the semi-classical limit, okay? All right? So what we have here is the quantum volume is in fact much larger than the volume per particle. This is what you call quantum limit bang, okay? You've got to be in the quantum limit here. Another possibility are electrons at the center of the sun. Okay? There, you find the temperature is 10 to the 7 Kelvin, and the number of electrons per unit volume is of the order of 10 to the 32 inverse meters cubed. And you can calculate then the quantum volume for the electrons at the center of the sun. That's 0.024 nanometers. Quantity cubed, that turns out to be 1.38 times 10 to the negative 5 nanometers cubed. And then you can also calculate the volume per particle. That's 0.022 nanometers cubed. So that's 1 times 10 to the negative 5 nanometers cubed. And you see when you compare these that the quantum volume is pretty close to the volume per particle. But definitely doesn't satisfy this. Quantum volume much, much less than the volume per particle. So this one also would have to be, these electrons would have to be treated in the quantum limit. And all we mean by the quantum limit is we worry about whether our particles are fermions or bosons, in this case fermions. Okay? So imagining we have one of these systems, I'm going to focus on conduction electrons in a metal. We know we have to account for the fact that the electrons are all identical fermions and therefore obey the Pauli exclusion principle. So we're going to write down what we know about the ground state of these conduction electrons. Okay? So we're going to model the conduction electrons in copper as a quantum Fermi gas. And by the way, as you'll see, I'm going to say it's in its ground state, which means basically T equals 0. Your first inclination to that ought to be, what? T equals 0? You're at room temperature, 300 Kelvin over here. Well, we'll see in a minute why it's going to be reasonable to treat that as T equals 0. That means I know, let me plot the Fermi, let me sketch for you, the Fermi-Dirac distribution function for fermions, obviously, as a function of the energy levels that are available. And the occupancy only ranges between 0 and 1. And here's where you have the chemical potential somewhere. And the point is that this is a step at the chemical potential when you're at low temperature, 0 temperature. Okay? And all the single electron states with energy epsilon less than the chemical potential are occupied, and all single electron states with energy greater than the chemical potential are unoccupied. Okay? That's pretty much, that's going to be it with just a little bit more. Okay? One other thing I'm going to mention here, this one is more of a historical note. It's a convention to call the chemical potential, to name it, at 0 temperature. The chemical potential at 0 temperature is called the Fermi energy, symbol epsilon sub F, of the gas. Okay? In other words, by definition, the Fermi energy of a degenerate Fermi gas is the value of the chemical potential of the gas at 0 temperature. That in this picture is going to be right here. Because this is the 0 temperature graph of the distribution function. And so the chemical potential, where the step is, this is, by definition then, the Fermi energy of the degenerate gas. Okay? Okay. So all we do then, guess I have two, aren't I? Is we just basically have to keep track of what the single electron states are that are available to our electrons. Okay? We think of our metal as being, let's just take it a simple cube. That's our metal. Okay? It's a box. Okay? So we've got our various dimensions, x, y, z. Each dimension is L. Okay? And our free electrons are inside that box. There's a lot more going on inside that box that we're ignoring. We're just imagining electrons roaming around inside that box. And we solve Schrodinger's equation. Okay? But that's the particle in the box problem. We've done that already. Remember, you get standing wave solutions to Schrodinger's equation? And you get 3 separate standing waves, one for each dimension. You get a standing wave along x, and a standing wave along y, and a standing wave along z. Okay? So from Schrodinger's equation, you can list what the allowed momentum components are for these standing waves. And you get h nx over 2L, where nx is a quantum number for the standing wave along the x direction. That's to give you the allowed values of p sub x. And for p sub y, you'll have h times another quantum number n sub y over 2L. And for p sub z, you'll have h times a third quantum number n sub z over 2L. Okay? 3 independent quantum numbers. And then based on that, you can write down the allowed energies that go with these individual electrons moving around inside the box. That's the single particle energy, so that's epsilon. But it's going to depend on these quantum numbers, because if they're just free electrons roaming inside the box, then their energy is only kinetic, so it's the magnitude of the momentum squared over 2 times the mass of an electron. So that's px squared plus py squared plus pz squared over 2m. And then plug in these expressions for px, py, and pz. In here, square them, add them, factor out common terms out front. You'll have h squared over 8ml squared times mx squared plus ny squared plus nz squared. That's our first equation. So this is going to give me, when I put in various allowed values for nx, ny, and nz, it's going to give me the allowed single particle energies. And the electrons are just freely moving around inside a box. Okay? So now we just have to start doing counting. Okay? What is going to be the ground state if I have capital N electrons in this box? Okay? Well, I start with the lowest energy values I can have, and I start putting electrons into these energy levels. Okay? So let's draw a picture here. Okay, open my last number there, 2. Okay. So we'll draw a picture here of what your author would call n space. He's just going to have 3 axes, nx, ny, and z. And a particular point, say right there in n space, technically has to have coordinates where each is an integer. Right? So that would correspond to nx equals 2, ny equals 2, and z equals 3. Okay? And that one point in n space, okay, well, that represents a state that is available, okay, to an electron. In fact, now if we're really going to talk about a real system, I can put 2 electrons in that state. I just picked one of them, understand? Right? You can put 2 electrons in that state. One spin up, one spin down. Okay? So this is one point equals 1 allowed single electron state. It can contain 2 electrons if they have opposite spins. One spin up, one spin down. Okay? So how do we get the ground state? The state for this whole system of capital N electrons with the lowest possible energy? Well, I start at the n values closest to the origin that I can get. Because the smallest n's I can have there correspond to the smallest epsilon. Okay? So, right? So I get as small as I can, and smallest point closest to the origin, I put in 2 electrons. Then I just start working my way out, going ever higher in energy, for each state putting in 2 electrons, until all capital N electrons have been assigned a state. Okay? All right, so at 0 temperature, the states start with points near the origin and fill each with 2 electrons, going up in energy as you go, until all capital N electrons have been assigned a state. And the key thing to note is that capital N here is going to be a large number. Right? It's going to be of the order of 10 to the 23. Okay? It's going to be of the order of 10 to the 23. That means there are going to be a huge number of these states I'm going to have to be working with. Right? Starting here close to the origin and working my way out, filling in 2 electrons in each state, allocating up to about 10 to the 23 of these electrons, that's going to be a huge number of those dots. Huge number. So many that if I were to zoom out so that I could see the ones that were occupied, they would look continuous in n space. I wouldn't see the discrete points. I would just look like all of n space was filled. At least in the region here where I'm allowed to be, which is nx, ny, and nz positive. So if we change our scale now on our picture, zoom out so that I can see all the states that are filled, then what it will look like is that I have 1/8 of a sphere, or a spherical surface. Okay? And that pretty much everything inside here going in towards the origin, in this 1/8 of a sphere, are occupied states in n space, each with 2 electrons. So I think of this now as a continuous volume. All right? I have, in fact, an octant of a sphere. I have 1/8 of a sphere. Okay? And this sphere has a radius that I'm going to call little n max. That would be the point here, and here, and here, where the sphere intersects the axis. Right? That's the radius. There, and there, and there. Right? Just imagine it's 1/8 of a sphere, and that radius is n max. I'm going to have to figure that out, but there's some radius to this sphere. And every state with n max or less going down to the origin is occupied by 2 electrons, and every state above that is unoccupied. Okay? So now we just do counting. Okay? I basically have a continuous volume of states. So the total number of electrons is going to be 2, because each state in here can hold 2 electrons, times the volume of 1/8 of a sphere. Right? The volume that's inside there. Okay? 1/8. Sphere of radius n max. That's just counting. So that's pretty easy to write an expression for, because I know the expression for the volume of a sphere. It's 4/3 pi times the radius cubed. So I'm going to take that and divide by 8, and then multiply by 2. And that must equal the total number of electrons that I've been allocated into states. Okay? So capital N will be 2 times 1/8 times 4/3 pi n max cubed. And then what I do, of course, I simplify this. 4 times 2 is 8, and there's an 8 downstairs, so those all cancel. So I have from this that the total number of electrons is equal to pi times n max cubed over 3. Equation 2. Just comes from counting. That's how you're going to determine the radius of that portion of a sphere, the n max, by how many electrons you have. Okay. The next thing the Fermi energy of the gas. That corresponds to the energy of a single particle state on the sphere's surface. Why? Because at t equals 0, chemical potential is the same as the Fermi energy. That's the highest single particle energy level that's occupied. Or basically, it's actually the boundary between occupied and unoccupied. Well, that's the surface of this sphere when you're in this picture with n space. Okay? So here, we're just going to use equations 1 and 2. The Fermi energy from equation 1 is h squared over 8ml squared times, well, that's the distance squared you are from the origin. Well, that's n max squared. Okay? So h squared n max squared over 8ml squared. And now substitute this expression here, use this expression, equation 2, for the n max. Right? N max is 3 times big N over pi to the 1/3. So you'll have this expression then. H squared over 8ml squared, 3 big N over pi to the 2/3. Then all I'll do to help see what this value of the Fermi energy is I'll take this L squared inside here. Okay? It gets raised to the 2/3. You got to make sure you end up with L squared when you do it. So you have h squared over 8m. Then you've got 3n over pi. You got to have then, when you take it inside, L cubed. So that is equivalent to L squared downstairs. But L cubed is just the volume of that box. My sample, my metal. That was a piece of metal. And my electrons were moving around inside it. So that's just the volume of the box. This is h squared over 8m, 3n over pi times the volume to the 2/3. And that's the expression for the Fermi energy of a degenerate Fermi gas. And it's general, by the way, for any shaped box, not just a cube. Just put in the volume. Notice, in fact, though, that the Fermi energy, it really doesn't depend on just N or just V. It depends on the ratio of N to V. Well, that's the particle density. That's an intrinsic property of the material you're studying. So Fermi energy is an example of what you would call an intensive property. Not extensive, but intensive. It doesn't depend on the size. Okay, then come just a series of results. Okay? Like I said, I'm going to scan these part of my notes and put them on Blackboard so you can see the math. I'm just going to tell you some of the results you get. Probably one of the things you'd like to know is, what is the total energy of the degenerate Fermi gas? I know what my ground state looks like when I look at it in space. I have all the states in n space that are within this eighth of a sphere occupied by 2 electrons and a very sharp surface, and all the states outside unoccupied, 0 temperature. So then I can ask things like, what's the total energy? The Fermi gas. We'll use the symbol U for that. All you got to do is you got to go to each one of the little dots in there that is an allowed value, allowed point in n space, and say, hey, what's your energy? And you have 2 electrons. So for every one of the dots that's allowed in here, take the energy of that state and multiply it by 2 and add them all up. Okay? So this will be, I'll start like this, 2, sum over all the values that are allowed for nx, ny, and z, the energy, which is a function of nx, ny, and nz. Of all the states inside that sphere. Okay. And the ones down in here near the origin have smaller energy, and the ones up here near the Fermi surface have larger energy. Now what you do is you say, yeah, but when I'm out here looking at this, there are a huge number of those dots in there. So many that I'm going to convert that to an integral, triple integral. An integral over dnx, an integral over dny, an integral over dnz. So dnx goes from 0 to n max, and an integral over dny from 0 to n max, and an integral over dnz from 0 to n max. The energy as a function of nx, ny, and nz. Then you just have to remind yourself, what is that expression for the energy? Well, that's h squared over 8ml squared times nx squared plus ny squared plus nz squared. But that's just the distance squared you are from the origin. So most people will just write that like this. N squared, where that means the magnitude of this n vector, really, squared. Okay? It's just the radial distance you are in n space from the origin. Since the energy only depends on the radial distance from the origin, you really want to convert that integral to spherical coordinates. And then do the integral in spherical coordinates, integrate over an entire sphere, but divide by 8. Okay? And that's what you do. All right? Again, you can look in the notes. I'll just write down what you get. 2 times h squared over 8ml squared times 1/8. You'll have an integral from 0 to n max of n to the 4th dn. And then whenever you do spherical coordinates, you have the polar angle theta and the azimuthal angle phi. So there's an integral over sine theta d theta and an integral over d phi. Right? And those of you that have done E&M, I know you know about integrating in spherical coordinates. Okay? And these two angular integrals together just give you a 4 pi. The two angular, this one gives you a 2 pi, and that integral there is a 2. So the product of those two integrals together is 4 pi. And then you simplify that, right? And you got that integral there. Oh, I'm sure you're looking at that thinking, what's that? Then, if you're not sure why it's n to the 4th, there's an n squared from the energy. And then when you convert the integral to spherical coordinates, you pick up another factor of n squared. Okay? That's why it's n to the 4th. So you do that last integral right there, n to the 4th dn from 0 to n max. You got these constants out front. It becomes pi h squared over 8ml squared n max to the 5th over 5. Okay, now the next little trick, just a little aside here. N max to the 5th is, certainly, n max cubed times n max squared. That's certainly true. Why write it that way? Because I'm going to use two of my earlier expressions. For the n max cubed, I'm going to use equation 2. And for the n max squared, I'm going to use equation 3. See, the n max cubed is proportional to big N, the total number of electrons. And the n max squared when I write it N max squared, when I say use equation 3, I mean here. N max squared is proportional to E Fermi. So when you substitute those expressions in for U, you get pi h squared over 8ml squared times 1/5, there's a 1/5 there, times from the n max cubed, 3 capital N over pi, times from the n max squared, 8ml squared times the Fermi energy over h squared. And you simplify, right? You got pi h squared, 8ml squared, 8ml squared. This is simplifying a lot. 3/5 times the total number of electrons times the Fermi energy. That's the total energy of the whole set of n electrons. Take 3/5, the maximum energy, and multiply by how many electrons you have. Another way to say it is what's the average energy per electron? Or whatever your fermion is. The average energy per electron is the total energy over the number of electrons, U over M. So that's 3/5 times the Fermi energy. So the average energy of the electrons is a little less than the Fermi energy. Well, it should be less because the Fermi energy is the maximum energy that any of the electrons can have. So the average energy of them has got to be less than that. It's got to be less than the maximum. And then you define one more thing. The Fermi temperature of the degenerate gas, T Fermi. And that's merely defined like this. Boltzmann's constant times T Fermi is defined to be the Fermi energy. In other words, the Fermi temperature is the Fermi energy over Boltzmann's constant. You can do other things, I will just tell you for the sake of time. You can do things like calculate the pressure of the degenerate Fermi gas using this expression, negative partial of U with respect to V at constant S and N. And you can write the internal energy U in terms of the volume and then take that partial derivative and simplify it as much as you can, and I will tell you what you get. 2/3 the total energy over the volume. This is called, by the way, the degeneracy pressure of the Fermi gas. This gas of electrons resists being compressed. So therefore, it must have some equivalent pressure. And this is how you would calculate the amount of it. I'll tell you a value for copper in just a moment. This pressure comes purely from the exclusion principle and not allowing you to put all the fermions in the same single particle state. Okay? This degeneracy pressure is what keeps matter from collapsing in on itself. Because otherwise you should say to yourself, well, I've got electrons, if I just think of an atom, I've got an electron that has negative charge, and the nucleus has positive charge, and opposite charges attract. So it ought to collapse in on itself, the atom. And so matter ought to be collapsed in to a much smaller scale, the scale of a nucleus. Right? Well, that would be a very different kind of universe. Something is preventing that from happening. It's the degeneracy pressure from the fact that you have a bunch of identical fermions. Okay? So, again, I'll put this all on Blackboard, but just to give you some numbers. if you calculate these various quantities, oh, there's one more thing you can calculate. The bulk modulus. That's how hard it is to compress the gas. It's under pressure now, so we know it's not going to be easy to compress it. You get that by doing this derivative. Okay? To get the bulk modulus. For the Fermi gas, you express the pressure in terms of the volume, and you take the partial, and you simplify it as much as you can. You get that, 10/9 the total energy over the volume. Not obvious, but that's what you get. Now that's the contribution to the bulk modulus, how rigid it is, purely from the fact that these are identical fermions. Purely from that. And the exclusion principle. Resisting being compressed. Okay? Okay, so what are some numbers, just so you have a sense, for, let's say, copper? Okay? So you can do some basic counting by using the known mass density of copper and the atomic mass of copper. Okay? Pretty well-known values. You can use one other fact, and that is when you make a sample of copper from copper atoms and put the atoms in a lattice, every atom contributes one conduction electron. Okay? Copper contributes one conduction electron per atom that then can freely roam around. Okay? So with that in mind, you can figure out how many conduction electrons there are per cubic meter in copper. Any sample of copper of any size, and you get almost 8.5 times 10 to the 28 electrons per cubic meter. Okay? It's a very large number of free electrons in a cubic meter of copper. Then, with that information, you can calculate the Fermi energy. Right here. Okay? Because I just told you the density of the electrons. That's the N over V for copper. And of course, the M there is just the mass of an electron. And so when you calculate the Fermi energy for copper, you want to do it in electron volts, 7.06 electron volts. Now that may not mean much to you because you're not used to thinking in electron volts. So then you can also use the Fermi energy to get the Fermi temperature of the conduction electrons in copper. That's 81,900 Kelvin. So when the sample is at a temperature considerably less than T Fermi, you can assume it's in its ground state. Well, T Fermi is 81,900 Kelvin. And I'm talking about a piece of copper sitting here in a room at most 300 Kelvin. Well, as far as that's concerned, 300 Kelvin is essentially zero. Okay? So your sample of copper, to the first order analysis, you can say it's in the ground state of the degenerate Fermi gas. That won't get you everything you want to know about copper. Eventually you will have to say, okay, let me look at some of the excited states too. But you don't have to do too much with the excited states. Ground state gets you a good start. Okay? All the electrons right up to that Fermi surface occupied, every electron or every state above that unoccupied. And that's a sharp, sharp, sharp surface. That's the ground state. Okay? As the temperature goes up, that surface starts to blur a little bit. As some states below the surface start to become empty, and some states above the surface start to become occupied. But knowing the Fermi temperature, that tells you whether or not you're close to the ground state. So 300 Kelvin for copper, room temperature, a lot less than the Fermi temperature. A lot less. What's the degeneracy pressure for the conduction electrons in copper? I'll tell you in terms of atmospheres. Right? We're here at 1 atmosphere from Earth's air on top of us, 1 atmosphere. The degeneracy pressure from the conduction electrons in copper is 380,000 atmospheres. Okay? Now what you can actually measure is the bulk modulus. So if you measure the bulk modulus First of all, if you calculate using that formula for copper, okay, then that is 6.4 times 10 to the 10 pascals. Remember, 100,000 pascals is 1 atmosphere. Measured bulk modulus for copper is 13.43 times 10 to the 10 pascals. In other words, for this, you get about half the measured value. Well, that must mean there are other things inside the copper that are contributing to the bulk modulus. There are, after all, the lattice of the nuclei with their remaining electrons. They resist being compressed too. Okay? But notice that the bulk modulus from just the identical fermions, the electrons, get you almost half of the measured bulk modulus of copper. So they make a significant contribution to it. Okay? So those are just some numbers that you're starting to do, by the way. I mean, this is real stuff now. This is starting to study a chunk of a very common metal, copper. Okay? So you're starting to really, really do physics when you start to do this kind of stuff. Okay? So if you go to grad school and you do StatNet, or maybe take a class in condensed matter physics or solid state physics, then you'll learn how to, this will be the first thing they do. And then you'll learn how to start putting in some of the low-lying excited states as well. Okay? Okay, so, and that's the next thing I would have done. Remember, normally I would have had another week of classes on the old calendar. So I would have talked about how you start bringing in the excited states, the low-lying excited states. We would have introduced the concept of what's called the density of energy states. That's a very important concept in physics. Then we would have looked at quantum statistics for bosons. And we would have looked at photon gas, black body radiation, and a phonon gas. You ever heard of that? Those are quantized lattice vibrations, like in the Einstein solid. Quantized lattice vibrations in a solid are called phonons, because they are in essence sound. Okay? So and those are bosons, so we would have done those. And then I would have ended with Bose-Einstein condensation. But that's just, I guess, a teaser, because I'm not going to be able to actually do those things. So the final is up through those pages in chapter 7 that I mentioned. Okay? Up to page 277. Okay.